So we left off with question 17.11. We finished the first two problems, and I said we were going to save these last two, C and D, for today. So I'll erase that. Okay, so just to review, okay, we're trying to determine whether these compounds are aromatic, non-aromatic, or anti-aromatic. Now remember, anti-aromatic is highly unstable. Highly unstable. And so a compound will do anything it can to avoid being anti-aromatic. If there's no choice, well, then it's going to be anti-aromatic, but oftentimes it will do whatever it can, okay? So if we go back to the first one, the reason this compound is anti-aromatic is that lone pair is going to be in an is going to be in a p orbital, right? Because it's going to be resonance stabilized, right? You could draw a resonance structure like this, okay? But when we count up the total number of electrons in our continuously overlapping system of p orbitals, we have a total of 4. So that's an even number of pairs, right? So that would be 2 pairs, which is an even number. So that would mean the compound A, that anion, is anti-aromatic. When you go to the next one, the carbocation, again, everybody knows, or you should know, that this carbon with the positive charge is sp2 hybridized. So therefore, it has a p orbital on it. This carbon and this carbon, those are also sp2 hybridized, so they have p orbitals. So do we have a continuously overlapping system of p orbitals? Yes, we do. Now, is it a Huckel number of electrons that are in our continuously overlapping system of p orbitals? Well, we've only got 2, the 2 electrons in that blue pi bond, and so therefore that is a Huckel number, 4n plus 2, when n is equal to 0. 4 times 0 is 0, plus 2 gives you 2, and so this is an aromatic compound. If we go to the next one, okay, if we look at C, well, in C, right, every single one of these carbons is sp2 hybridized, right, because they all have a steric number of 3. And then also, you guys know that a carbocation is going to be sp2 hybridized. So that means throughout this entire molecule, we have a continuously overlapping system of p orbitals, okay? So the first criteria is met. I'm going to delete those p orbitals that I drew, but the first criteria is met. However, if we count the total number of electrons in the continuously overlapping system of p orbitals, we have 1, 2, 3, 4. So is that a Huckel number? No, because 4 divided by 2 gives you 2, which is an even number. And so we have 4n, where n is equal to 1, because 4 times 1 gives you 4, and we have a total of 4 electrons, okay, in our continuously overlapping system of p orbitals. And so this is anti-aromatic. Anti-aromatic. In fact, this carbocation is so unstable, I don't know if it's ever been made, okay? I don't think it's ever been isolated. All right, let's look at the next one. Okay, same thing. Could we put this lone pair in a p orbital? Yeah, because it could participate in resonance like that. But let's ask ourselves, if that lone pair was in a p orbital, okay, let's imagine it was, every other carbon in this ring is sp2. Therefore, we would have a continuously overlapping system of p orbitals. Therefore, the first criteria is met. Now let's count the total number of electrons, okay? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we have 10 electrons participating in our continuously overlapping system of p orbitals. Is that a Huckel number? The answer is yes, it is a Huckel number. It's 4n plus 2, where n is equal to 2. 2 times 4 is 8, plus 2 gives you 10. And so this anion is an aromatic anion. So there you go. We've solved all 4 of these. The first one is anti-aromatic, second one aromatic, third one anti-aromatic, and the last one is aromatic as well. Now, there are other questions. I think there's other parts of this one, so I would recommend that you try that use the solutions manual to help you with those. Maybe these are all the ones that are in this one. But anyhow, I digress. Then I said we would tackle the rest of question 17.13. And remember, when we're looking at lone pairs in a heterocycle, like this one here, okay, I'm going to review what we went over last class. If you look at this oxygen, you might have the knee-jerk reaction where you would say, well, this is sp3 hybridized, right? When we have H2O, right, the oxygen has 2 bonds and 2 lone pairs. And so you might think, well, that oxygen in water is sp3 hybridized, so this oxygen in the ring is sp3 hybridized. Well, in this case, Let's imagine that if we were to put one of the lone pairs in a p orbital, okay, if we did, then we would have a continuously overlapping system of p orbitals. Would it be a Huckel number? 1, 2, 3, 4, 5, 6. So is that a Huckel number? Yes, it is. It satisfies 4n plus 2 when n is equal to 1. Okay, so somebody just asked me, what does the n represent? The n is just an integer. Okay, n can be 0, 1, 2, 3, 4, 5, 6, all the way up to infinity, I suppose. Well, maybe not. But anyhow, it's just a number. That's all it is. It's just a number. When you plug any of these numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, in this formula, and that formula spits out the number of electrons that are in your continuously overlapping a system of p orbitals. If it fits the formula, then it's aromatic. Does that help? Okay, it's just a number, nothing more than that. Okay, so let's look at the next one. Actually went over this one with you the other day. Okay, so if we look at our electrons, okay, so we have 1, 2, 3, 4. If we were to put 2 of the electrons on the sulfur, right, there's 2 lone pairs, but if we put one of the lone pairs in a p orbital and we change the hybridization of this sulfur, which looks like it should be sp3, but if it was sp2, okay, which would make sense because then these electrons could participate in resonance, okay. If they were in a p orbital, then we would have a continuously overlapping system of p orbitals. Would it be a Huckel number, 4n plus 2? Yes, it would be when n is equal to 1. 4 times 1 is 4, plus 2 is 6, and we have a total of 6. And so therefore, this compound is aromatic. All right, the next one. All right, so the next one, let's focus on the nitrogen. The nitrogen has 1 lone pair and 1, 2, 3 bonds like that. Okay, so what's something else that you know that has a nitrogen with 1 lone pair and 3 bonds? What about ammonia? Okay, a very simple molecule. It's the simplest possible amine. The nitrogen in ammonia is sp3 hybridized, but that lone pair is not participating in resonance. Could theoretically this lone pair participate in resonance? Look at this. Yes, it could. It's an allylic lone pair. So we have to determine whether the hybridization of this nitrogen is sp2 or sp3. If it was sp2, that would mean that this lone pair is in a p orbital. Every other carbon in the ring, or iPad, appreciate that. All the carbons in the ring, okay, all of them are sp2 hybridized, okay? So everything else in this ring is sp2 hybridized. So if this lone pair was in a p orbital, then we would have a continuously overlapping system of p orbitals. Now, let's count the total number of electrons. We have 1, 2, 3, 4, 5, 6, 7, 8. Is that a Huckel number? Does that satisfy 4n plus 2? No, it doesn't, okay? It satisfies 4n, where n is equal to 2. 4 times 2 is 8, right? We have an even number of electron pairs. So that would make the compound anti-aromatic. So you might think this compound is anti-aromatic, but hold the phone, okay? Remember, a molecule will do whatever it can to avoid being anti-aromatic because anti-aromatic compounds are so unstable. So how is this going to avoid becoming anti-aromatic? The nitrogen is not going to be sp2. It's going to adopt sp3 hybridization. So the lone pair will be in an sp3 orbital, and therefore the compound would not be anti-aromatic. It will be a non-aromatic compound. Okay? So let me write, I lost this one. So we'll just write in here 4n plus 2, where n is equal to 1. So this one is aromatic. All right, let's look at the next one. Okay, the next one, this is called thiazole. I showed you this, I think maybe at the beginning of the class or something. Okay, a couple of things. First, let's look at the nitrogen, because the nitrogen has a lone pair and a pi bond on it. Okay, so both of those, the pi bond, those electrons, and the lone pair, they both can't be in p orbitals, right? Because this nitrogen is sp2 hybridized, right? It has a steric number of 3. So that means that the lone pair is not participating in resonance. It has nothing to do with aromaticity, right? This lone pair has to be in an sp2 hybrid orbital. If you still don't know why, okay, it's because this is a pi bond. The pi bond is formed from the overlap of two p orbitals. There are not two p orbitals on the one nitrogen. There is only one p orbital on the nitrogen, which is making the pi bond. Therefore, the lone pair is in an sp2 hybrid orbital. So we'll put sp2 for this guy. So that means that there's a p orbital on the nitrogen, there's a p orbital on this carbon, and this carbon, right? All three of the carbons are sp2 hybridized. So now let's look at the sulfur. If we just highlight one of the lone pairs and say, hypothetically, let's ask ourselves, if this lone pair went into a p orbital, then we would have a continuously overlapping system of p orbitals. Then we count the total number of electrons. 1, 2, 3, 4, 5, 6. Is that a Huckel number? Yes. 4n plus 2 when n is equal to 1. 4 times 1 is 4, plus 2 is 6. And so this is an aromatic compound, okay? The lone pair on the sulfur, the ones that I have in blue, those are participating in aromaticity. Those are delocalized throughout the continuously overlapping system of p orbitals. But the lone pair on the nitrogen is in an sp2 hybrid orbital, which is perpendicular to the p orbitals. It has nothing to do with aromaticity. So the last question is this six-membered ring. We have an oxygen with a positive charge. Now, what is the hybridization of the oxygen? It has a steric number of 3, right? A lone pair, a double bond, and a single bond. Therefore, it is the oxygen is sp2 hybridized. We know that there is a p orbital on the oxygen, right? Because you have a pi bond right here. That's how pi bonds are formed. It's from the side-to-side overlap of p orbitals. Every other carbon in here is sp2 hybridized. So do we have a continuously overlapping system of p orbitals? The answer is yes. Absolutely we do. If we count up the total number of electrons involved in that ring of continuously overlapping p orbitals, 1, 2, 3, 4, 5, 6. Is that a Huckel number? Yes. It satisfies 4n plus 2 when n is equal to 1. 4 times 1 is 4, plus 2 gives you 6. And so this compound, or this cation, is aromatic. All right. There you go. Give me a thumbs up if you're even like 60% of the way with me on that one. Everybody? Okay. You are going to have to read it and practice it on your own. All right, cool. So that covers aromaticity. We looked at polycyclic aromatic compounds. For the final exam, I don't think you need to memorize the names of these compounds. However, sometimes they show up in the quizzes, and they do show up in the practice problems in the textbook. So I would memorize these three compounds, their names, because they are pretty common compounds: naphthalene, anthracene, and phenanthrene. All right, we don't study the chemistry of those a whole lot. Anyhow, so then we talked about reactions at the benzylic position. We talked about oxidation with chromic acid. We talked about how you have to have at least one proton. Right? You have to have at least one proton, minimum of one proton at the benzylic position. So we went over that. We said not only can you do it with chromic acid, you can also do it with under basic conditions. So you can also use potassium permanganate, water, and heat to do that. And then you end up with a carboxylate salt, with benzoate salt here. And anyhow, so then you have to acidify in the second step. So overall, it's 2 steps to do it with potassium permanganate. Anyhow, then we talked about free radical bromination at the allylic position with NBS and bromosuccinimide and heat. And we talked about all the synthetic utility of that last class. We talked about elimination, substitution, and how chapters like 12 and 8 can, come up because we're dealing with alcohols and things like alkenes. Okay. And then we said we would save this one question, so 17.17c for today. And it's just asking you what's going to happen if you treat this aromatic compound with chromic acid. So remember, chromic acid is formed in situ, which is Latin for in place. And so you can't buy chromic acid. You have to mix up sodium dichromate, sulfuric acid, and water. Okay. like that. All right. And so if we take a look at the three substituents, notice that you have a benzylic proton here, you have a benzylic proton here, but here we have no benzylic protons. And so that tert-butyl group is not going to oxidize at all. And so when we draw our final product, it's going to look something like this, where we're going to have a carboxyl group over here. We're going to have a carboxyl group over here. And then we're going to have a tert-butyl group over here, because that's not going to oxidize because it doesn't have a benzylic proton. All right. Then after that, we looked at the Birch reduction. So we talked about how you can hydrogenate an aromatic ring if you heat it up enough, how it's selective for alkenes that are outside the aromatic ring if you do it at a lower pressure and lower temperature. And then we said you can do the Birch reduction, which converts benzene into 1,4-cyclohexadiene. And the conditions are sodium, methanol, and ammonia, right? Sodium, methanol, and ammonia. So we said it goes through an intermediate called a radical anion. And I said, I'm not going to ask you this mechanism, but the radical anion is pertinent because it's got a negative charge. And so if you have an electron donating group, that carbon is not going to be reduced. Why? Because it's donating electron density, and it would be counterintuitive to put a negative charge there on the carbon that's highlighted in green if the R group is already donating electron density, okay? However, if you have an electron withdrawing group, something that is pulling electron density away, right? With a carbonyl, we have a dipole going in this direction. In that case, that carbon is going to get reduced, right? Because the anion that's formed is going to be stabilized by the electron withdrawing group, okay? And so you need to be aware of that. And with that in mind, that brings us to these last two problems here. We already solved 17.18c, so now we're into D. And this one is an interesting one because we're functionalizing at a tertiary carbon, right? This carbon is attached to 1, 2, 3 carbons, and then we're putting a methoxy group on it, okay? So remember, this is a benzylic position, okay? This is a benzylic carbon, and so that hydrogen that I just drew in red is a benzylic proton. And so the first thing that we're going to do is we're going to convert that to a benzylic bromide by using NBS and heat. So I'm going to see if I can squeeze this on here, but I'm just going to write pH for my aromatic ring. And there's my hydrogen. And so I'm going to treat this with N-bromosuccinimide, and I'm going to heat that up, and that's going to put the bromine in the benzylic position like this, okay? So now that I've got that in here, all right, the next thing that I'm going to want to do is I'm going to want to put in that methoxy group. So this one is it's not a complex reaction, but it's one that we don't think about a lot because we don't look at tertiary benzylic halides or tertiary alkyl halides nearly as much as we do primary, okay? So let me go back in my notes here, in the notes, and I'll show you what they're getting at with this problem, okay? So what they're getting at is this right here, okay? The reaction that we're going to use is going to be this one, where we take a tertiary benzylic bromide and we convert it not into an alcohol. In this case, we're converting it into an ether, but this is the famous solvolysis reaction, okay? So I'll show you. Let's go back here, and you can see it over here, okay? So if we do a solvolysis, you see where I have solvolysis in quotations here. So if we were to take this molecule, okay, and instead of treating it with water, if we were to use an alcoholic solvent like methanol, what that's going to do is that's going to form this, is you're going to have the methyl group in there. So that's a way of making an ether, right? The first step is the loss of the leaving group. You form a benzylic carbocation, which is highly stabilized, and then methanol can come in as your nucleophile. So again, that's what they're getting at in this problem. So all we have to do for the last step is just to treat it with methanol. Come on, iPad. There we go. So we're just going to take this compound and we're going to treat it with methanol, and that is the final step. Okay, it's not nearly as complex as you might think it is, like having to do anything extra special there. Okay, so the last one, notice that there's a change in the carbon skeleton here. We have 6, 7, 8, 9 carbons in the starting material, and then we have 8 carbons here, and then we lost 1 carbon, and we have a carbonyl. And so the way that I think about this problem is if I could make the alkene here, right, then all I would have to do is an ozonolysis reaction, and that would give me the ketone, right? Just treat it with ozone followed by DMS, okay? So now we just have to figure out how to make that alkene. But we know the first step is going to be to functionalize by converting it into a benzylic bromide. So we're going to treat this with NBS and heat, and that is going to give us this compound. So just bear with me. So we're going to have something that looks like this. Okay. So now that we have that, if we want to convert it into the alkene, what are we going to need? We're going to need some kind of base. Okay. It could be a hindered base. It could be an unhindered base. It doesn't really matter because substitution can't occur here. It can only be elimination, right? You're going to remove this proton, right, and then lose the leaving group. So I'll just erase that. So I'm just going to put sodium methoxide. Again, if you put T-butoxide, that's totally fine. That's going to give you, oops, that's going to give you the alkene. Okay, so that's going to give you the alkene like this. And then the last step is just going to be an ozonolysis reaction of an alkene. So step 1, ozone. Step 2, DMS. And there you go. So that's the whole kit and caboodle like that. All right, so with the next section, it says to skip the spectroscopy of aromatic compounds. I don't really think we should skip it entirely because aromatic spectroscopy or spectroscopy of aromatic compounds never goes away. So just thinking about IR, if you haven't thought about IR in a while, okay, so infrared spectroscopy, you should remember that when you have an aromatic ring, okay, so when you have an aromatic ring, you usually look for the sp2 hybridized carbon-hydrogen stretching. So that's shown here. It's usually right above 3,000. Then the overtones are usually between 1667 and 2,000. Students love them, okay? They're a very weak group of signals, but they usually denote that you have an aromatic compound. What I find the most useful for aromatics is the carbon-carbon double bond stretching in an aromatic ring. It says here it's between 1450 and 1650. It's usually 2 or 3 signals. And it says here 1450, 1500, and 1600, okay? And that could show up on the final exam. As far as the bendings go, I don't really worry about these ones a whole lot. The one in red and the one in green are the ones that are going to be most relevant to us, okay? You see the bending here on this one. But again, the main thing I'd want you to understand is that you have the carbon-carbon double bond stretching, you have the overtones here, and then you have sp2 hybridized carbon-hydrogen stretching in there. When you look at the NMR of aromatic compounds, so those protons for an aromatic ring, they usually show up somewhere between 6.8 to 8 parts per million. So usually it's a dead giveaway that you have an aromatic compound is when you have any signals up in that region, just above 7 ppm. And if you have a dye-substituted compound like this one here, and the 2 substituents are identical, X and X, well, in that case, all 4 of those protons are going to be chemically equivalent, and so you'd get a singlet. Whereas if you have 2 different substituents, X and Y, like this, in that case, you get 2 doublets, right? These two protons are chemically equivalent, so they resonate together, but they're both split by 1 proton, right? So N plus 1, so 1 plus 1 gives you 2, and the same thing would apply to those 2. And so that's why we see 2 doublets that both integrate for 2 protons. All right, for carbon-13, this is always kind of fun for students. It's just looking for planes of symmetry, and based off of symmetry, we can determine how many carbon signals we're going to have for our aromatic ring. I'm going to leave the section about graphite, which is an allotrope of carbon, which is just a bunch of aromatic rings fused together. I'll leave that as an FYI. I'm not going to test you on graphite, but you would have seen this in General Chemistry 1 when you looked at heats of formation, that carbon in the graphite form is the most stable form of carbon. So the transformation from diamond to graphite actually has a negative delta G, so it's a spontaneous process. And then Buckminster fullerene, this compound here, people call this a buckyball. The actual name of the compound is Buckminster fullerene. So if you take a soccer ball and then you put carbons at every vertex in there, and you get C60. Anyhow, also you can look into that if you want. And then the whole section about nanotubes, I'm not going to ask you anything about that. However, nanotubes are kind of cool in that there's so many applications for nanotube chemistry. Here you see, fibers and fabrics and biomedical applications. But again, I'm not going to quiz you on that. I'll leave that as an FYI. So that covers all of chapter 17. All right.